modeling CFP catalyst regeneration in BFCC units. A little bit of terminology. CFP is catalytic fast pyrolysis. Reddy actually alluded to that during his presentation. BFCC is a nomenclature we started using in Kior because I worked 8 years in Kior, and it was an FCC-based process, and that basically means biomass FCC. So it's not petroleum and it's not co-processing. It's running 100% biomass, okay? I want to acknowledge my co-authors at the National Energy Technology Laboratory, and I want to give a little bit of a shout out to the CCPC, which is the Consortium for Computational Physics and Chemistry. I always have to look because I, right? And in the CCPC, we're a multi-lab consortium of people doing computational modeling for the Bioenergy Technology Office. Okay. I am kind of the reactor scale lead for the CCPC. So there are those in the national lab system. I know some of you may share this opinion who are a little bit on the academic side. My career was spent entirely in industry until I joined Oak Ridge 6 years ago. So I've approached it from a very practical, let's get it done, let's accomplish something kind of an approach, okay? So enough said about that. Catalytic fast pyrolysis basically is a process where you start with a lignocellulosic biomass, okay? That basically means woody biomasses. It can be used for other biomasses, but I can tell you from experience that sometimes is a very, very bad idea. If you run, for example, algae in CFP, which has high nitrogen, you can make a product with 15% nitrogen in your oil, and that's the worst smelling thing that you've ever experienced. So it really is tailored for lignocellulosic biomass. Okay, in the ex situ route, which is what I'm showing you here, you have pyrolysis step. There is an in situ route. I'm not going to talk about it very much, but that was the Kior route, okay? But ex situ is all in vogue today. So you produce a pyrolysis vapor, which then goes into a catalytic upgrading step. And there is a catalyst, which the starting point was FCC catalyst, but they've evolved quite a bit since then. And since I've already said I worked for Kior, we tested over 2,000 catalysts in Kior, and there's still a lot of work to be done to optimize the catalyst when you think about how much optimization's happened in FCC over the years. You know, how much catalyst knowledge there is. Okay, you can use fluidized beds. My preference, of course, is the BFCC, but you could have a process that uses a bubbling bed or a moving bed, larger particles. You can do it in fixed bed. Our buddies at NREL, I'll be talking about in just a minute, have done quite a bit of work using a fixed bed upgrader. And there are advantages, of course, and disadvantages, as you would expect. I'm not going to talk about the product slate in each case, but what you want coming out of this is you want to maximize the carbon yield. You want to get as much carbon as you can in the usable products. You take the C5 plus, part of that, and you're going to treat it a little bit. It's still going to have quite a bit of oxygen in it. Okay, you're going to hydrotreat it and possibly hydrocrack it to make the gasoline, renewable diesel, synthetic aviation fuel, fuel oil, a broad spectrum of products that are possible. Okay, all of the data that I'm going to be talking about, and most of it in the National Lab System, has come from a unit at NREL. That's the National Renewable Energy Lab in Golden, Colorado. And that unit's called the 2FBR. It's a flexible catalytic fast pyrolysis unit. It has the pyrolyzer. Whoop. You told me not to do that, didn't you? He told me, don't push that button, it'll go black. You knew I would. Okay, that button, okay. So there's the pyrolyzer. You have a char cyclone, a char pot, a hot gas filter, etc. Okay, you have this flexible reactor that can be fixed bed or a bubbling bed, okay? But in the NREL design, it is set up for a Geldart-B type particle. Okay, this is not an FCC type particle. This is not an FCC type unit, okay? And then, of course, you have product collection, et cetera, et cetera. Well, in that unit, NREL in the CFP program over the past few years has tested fixed bed and fluid and bubbling bed catalysts, okay? They do have a DCR, which could be used for a real BFCC. There's issues about the way it's configured and has been for the past few years, and its availability on other projects and things like that. So we in the CCPC, especially me, I said, I want to use as much of the data coming out of this unit and try to learn something about what regeneration in a BFCC would look like, okay? So the team, the CFP team, oops, sorry, go back, has done extensive laboratory characterization of the coke catalyst with temperature-programmed oxidation, NMR, microscopy. We had quite a few people in the national labs working on that to understand that coke. It's a biogenic coke, and it's different than petroleum-derived coke. That's what is at the heart of this whole study, right? Do we have to modify regeneration strategies for biogenic coke? These particular particles, like I said, are Geldar-B. Very high carbon levels, 9 to 13% on catalyst. Obviously far higher than you would have in the FCC, but I'll come back to how we translate that. This particular formulation I'm talking about today is very high in ZSM5 and pretty low in alumina, and it's not a good FCC formulation. I'll show how I've taken that into account. So we're basically trying to use existing data to forecast into what we would expect in an FCC, in a BFCC unit, right, until we can get such time and availability to start doing the real research in a DCR type ECAT, okay? This is an advantage, having this much carbon on catalyst, because you have a really good signal-to-noise ratio. You guys who've worked with FCC ECATs, when you got 1% carbon on catalyst or less, you know, you got a lot of matrix and not much of the carbonaceous species, and so this signal-to-noise ratio is actually a big advantage. So what we did is we took the characterization, we took the TPO data, and there's been a lot of TPO data generated. I'm only going to show you a little bit of it, and developed kinetics for coke oxidation. The biogenic coke oxidation, okay, specialized kinetics. All right, and then I did the extension to the FCC catalyst with the Geldar particle with a much lower carbon on catalyst. Okay, COC means carbon on catalyst, coke on catalyst, wherever I'm using that expression. Okay, and the result being, let's model a BFCC regenerator in Barracuda. So yes, Barracuda is part of my presentation, but I've got several slides to go before I get to that point. Okay. This is an unpromoted catalyst, so it's just ZSM5 and a binder alumina. There's no phosphorus, which is something that we very early decided in the program we should study, because most ZSM5s are phosphated. Okay, it's a TPO. Okay, in this case, we're running 10% volume oxygen in helium. You can also, we've run down as low as 1%. This apparatus is at PNNL in Richland, Washington, and they've done a bunch of experiments for us. And here you can see what a typical TPO looks like, and you'll see two interesting things. Of course you see CO, of course you see water, and of course, what you don't necessarily, of course, see is this bimodal type combustion pattern. For this unpromoted catalyst, we saw that every time. There was always a high temperature. I started calling it the high temperature species. There's some form of carbon that only combusts at higher temperatures, okay? And that's important. We did some NMR and said, well, that didn't really teach us much. We know that almost all cokes on any catalyst in refining has aromatic and aliphatic constituents, right? You never have a 100% aromatic coke. They're always substituted to some extent. But that didn't really teach us anything about high versus low temperature coke. Okay, I use finite element modeling. In this particular case, it's COMSOL. I did a fair amount of COMSOL work to help deconvolute those TPO spectra. Now, you can take TPO software and you can back out activation energies and do peak decomposition, but I wanted to go a little bit further. So I did, for example, bed heat transfer studies. You know, this is a very exothermic thing to be doing in a TPO, right? And so we had a silicon carbide bed and mixed with the catalyst with a before and after silicon carbide bed. And what we proved is that you actually need that before and after bed and the heat transfer characteristics of that bed and the heat transfer to the wall to be able to actually avoid a temperature hotspot inside the TPO bed. And that was important to make sure that our experiments were robust, right? Now, another thing that went into the TPO finite element modeling is I tried to do the best job I could within reason, right, of accounting for the porosity loss due to the coke and how that porosity is regained as the coke is combusted away. And how does that affect on the apparent kinetics? And all these things, remember, we're talking about trying to go from apparent kinetics to intrinsic kinetics, okay? Physical distribution of the coke. This was an interesting one. Here you're looking at cross sections of these coke catalyst pellets, and you see some of them are very clear core shell. Some of them, they look like they're not, but you know what? Look at this. We've basically just sectioned through the upper portion of these pellets. So you probably missed the core. So we said probably these things are essentially all a core shell carbon deposition. Why does that happen? In my mind, I'm a catalyst guy for decades. It's very simple. I've got too much ZSM5. I don't have enough mesoporosity. I don't have enough matrix. It's decomposing very quickly, and the heavier molecules are not even seeing the core. Okay? And that needs to be taken into account when you do the kinetics extraction. And the other thing that we learned from this, and this I knew from my FCC days, there's no coke inside the zeolite crystals. Okay? ZSM5, you can't get anything bigger than a 2-ring aromatic compound inside those micropores. You don't expect coke inside the pores. That's important. It teaches us which pores do we actually want to model to do this deconvolution. Okay? And it is possible, of course, in COMSOL to model core shell coke profiles. Relatively trivial. I did a bunch of it. And you can see here some of the issues as, you know, in this particular case, assuming a low coke density, you know, our matrix pores are down to 6 nanometers or smaller, and then as they combust away, they're back up to the fresh catalyst of 34 nanometers. Well, that has a big effect on gas diffusivities. In this case, in this example, it's holding the CO in that region. The diffusion is not sufficient to remove it, and it's actually further reacting away. Okay? All of these things can obfuscate your kinetics, and that's why I wanted to do everything in the finite element model to try to make sure we had the best kinetics we could from the TPO. And we also back these up with crush catalysts, of course, to be able to feel confident in our kinetic model. And here that kinetic model is. Okay, it's fairly complicated compared to what most regeneration models would look like. You have a low temperature CO2 and a high temperature CO2, a low temperature CO, a high temperature CO, and these are written as surface reactions, okay, with concentration on a surface basis, because when we want to compare different catalysts with different matrix surface areas and things like that coming out of the TPO experiment, this is the best way to do it, right? But obviously, once we translate this to Barracuda, as you'll see in a little bit, that's going to take a little bit of work. And then here's our CO oxidation reaction. Okay, and it's a homogeneous reaction, so it's a volumetric. Okay, and then here's a list of parameters, which, you know, it's a pretty big list for a kinetic model, and I don't want to say that it's completely unique and absolutely correct, but I do want to say is that we've tested it over many, many different TPO spectra under different conditions, and it's a good model, right? So we've all heard the expression, no model's correct, some are useful, right? This one is very useful. Just some data to show you here. This is 4 TPO runs I picked, okay? with differences in the oxygen concentration and the temperature rate, right? Scanning rate. And here's the CO2 and the CO from the data, and here's how the model predicts, okay? So without looking at a whole bunch of statistics and R-squared or whatever you want to look at, basically, and this is in the time domain, okay? So you look at it in both temperature and time domain, and this fit is good. This fit is absolutely good enough for the work that we're wanting to do here. And here's a couple of places where you can see some points of concern. 1% oxygen, we haven't even finished it at 700 degrees, right? And 5% oxygen, now here's a faster scan rate, but you see we had a number of different TPO spectra where we said, wow, we haven't even finished combusting that at 700 degrees. Well, that's important. It's telling you that that high temperature species is real and needs to definitely be considered, okay? Now, to translate the model to Barracuda, I basically took particles with an 80 micron, this is a D50, and I said, these are going to be about 1% carbon on catalyst, not 9 to 13%. And why is that? Well, of course, the particles aren't seeing the kind of residence time as they are in a bubbling bed. You know, they're inside an FCC unit. And all FCC units run with low carbon on catalyst, right? And so the issue was to translate. All right, and remember, this is basically a computational exercise to get some idea of what we might expect. Okay, we are planning to do at some point the DCR tests, which will be fun to see, did this approach actually work, right? So the first assumption to be made is that the Koch profile inside the particles is uniform, so we're not going to try to model the particle interiors, okay? Why do I rationalize that? Number one, because our data already shows us at small particle sizes, the FEM model shows almost no difference at the lowest high Koch densities, even at high carbon on catalyst, okay? At 1%, one would argue it's probably going to be more uniform than going all the way to 13%. And this is the one that I alluded to before. That catalyst has too much ZSM5 and not enough alumina. And that core shell Koch profile is reflective of that. And back in the day, many, many moons ago, I did studies like this in FCC where I said, how much zeolite can I put in there and how much matrix and how much of that zeolite can I actually see the effect? My rule of thumb was, you're wasting your time above 50%. For the matrices that were common for FCC catalysts, don't try putting more than 50% zeolite in there because you're wasting money, okay? And so because of that, I felt comfortable saying we're going to assume that this is a uniform Koch profile in these particles, and I'm not going to have any changes in the pore structure because the carbon amount is so small and it's uniformly deposited, so I'm not even going to worry about what's happening inside those particles, okay? And then I convert the reaction expressions to volume concentrations instead of surface concentrations. And I did that with scratching out the math, and then I validated it using the single particle in one grid cell method that's in the CPFD training manual. So, way to go, guys. That worked beautifully. We did that with COMSOL, we did that with Barracuda, and we actually even did it in MFIX. This method is good. I love it. And gives quick results, okay? So here's the translation that we made. And it's just in the rate constant parameters, okay? The exponents don't need to be changed. The activation energies don't need to be changed. Just those rate constant parameters need to be changed, and essentially by a constant, all right? And it represents, I got really close to being able to pencil that out and saying why that is. I didn't get 100% of the way there. Yeah, I didn't get 100% of the way there, Peter. Okay, but I got really close. But this test just nailed it. I did it for a bunch of cases, and it's a solid translation, guys and gals. Okay, now we're going to talk about Barracuda and regenerator modeling. Now we picked a very simple regenerator that has a catalyst inlet, a catalyst outlet down here, and a flue gas outlet, okay? This is a 5-ton per day demonstration unit scale regenerator. I'm not going to tell you how I know that this is a viable design, but this is a viable design. And then here's some of the things that we fixed, also based on viable information, okay? The biomass feed rate, 5 tons per day, the catalyst circ rate, your cat to biomass is 9. Now, that's way higher than FCC. And that is needed in BFCC, okay? You're no longer just evaporating and converting VGO or even resid. You're actually physically converting solid particles. You need a lot of catalyst in this process. So the cat circulation rate is 45 tons a day, right? Which works out to about 1/2 kilo a second, okay? When you look at our base catalyst inventory, we decided we needed, to, because of a little bit scary about the high temperature species, that we needed a lot of residence time. So we started out with a bed basically at that level, which would be 300 and some kilos. So, you know, the nominal turnover of that bed is 600 seconds, 10 minutes. So that was by choice. We wanted to start with those kinds of long residence times and then see where we ended up, okay? You can see the other, I do have the low and high temperature form of carbon, 1% coke on catalyst, since we've got 9% coke yield. There again, that's much higher than FCC. Everybody knows that. You're going to make more coke. And divided by the cat to biomass, you've got your 1% carbon on catalyst, okay? And here's some other information about stoichiometric airflow. Nominal pressure is 274 kPa, so it's not atmosphere. It's close to 2 atmosphere gauge, okay? Which most of my experience with DCRs and other units like that is, oh yeah, most of them are running at 20 PSI, you know, something like that. So, okay, that's sensible. Catalyst particle density and then the actual PSD. This is a real catalyst, ladies and gentlemen. And in fact, a real catalyst that has been used in a real process. Okay, in doing this study, what are we studying? Well, first of all, the why. I want to see the carbon on catalyst, the coke on catalyst of the ECAT. That's important because that sets the activity of the catalyst that's going back to the riser, right? I mean, ideally, you would remove all the carbon, but no FCC regenerator does that. Most of them will leave 0.1% or something like that, okay? But that sets the activity of your returning catalyst. And then, not so much for the demo unit, but you know, we should be thinking about afterburn. In the TPO, we clearly saw a lot of CO evolution. Well, in a real unit and a big unit, if the CO isn't combusted in the bed and it can make it to the freeboard and it can meet oxygen, free oxygen in the freeboard, you can have that combustion in that freeboard, and that's called afterburn. And you can have very high regenerator head temperatures. I actually toured a regenerator, I can't tell you where it was, a big one, running 140,000 barrels a day. I walked in between the stripper and the regenerator, and they had like a 10-inch steam pipe blowing live steam on top of the regenerator, and I got within, I don't know, 10 feet of it. I said, I'm out of here. You know, I can't do that. Why are you doing that? To cool the regenerator head with live steam, because the thing was constantly in afterburn. Okay, and then that's where catalyst companies can sell catalyst promoters, and we always like that because, you know, we can make good prices for combustion promoters, right? So we want to do at least get some indication if that's going to be an issue, right? Okay, typical solution behavior. Remember, this is a long residence time, 600 seconds for one turnover, okay? So far, I'm not finished yet coming up with the best strategy. I've been trying to set, the initial conditions of the bed as close as I could to where I think the bed's going to end up, as you would logically do. I think there's still more work to be done. But you can see here, this is a 2400 physical second simulation, and you can say, yeah, okay, we're pretty much at steady state there. Even though, so it's interesting, the CO is still coming down, right? But, don't be too alarmed by this. This is kind of because we've set a real long residence time in this simulation. Although I would love to work with you guys to see if I can speed this up a little bit, because this booger runs about 300 seconds per day. Okay, so you're talking about 8-day simulations, right, on my workstation. Yeah. It's still not alarming because I've got the 3 licenses running and the project's going. Okay. So what comes out of that? Here's that carbon on catalyst that we're interested in. Basically, I need to point out one thing. The variables I used were the relative airflow. Remember, one is stoichiometric. So what if we go deep into full burn? Okay, excess oxygen, right? Relative catalyst inventory. If I increase my catalyst inventory even more residence time, what will that do? And then I use decat temperature as an easy way to say, well, riser outlet temperature, which actually would be stripper outlet temperature, and or a catalyst cooler, which for units burning this much carbon, you're probably going to have a catalyst cooler. So that's the way I took that into account, more or less, is just by adjusting the temperature of the incoming spent catalyst. Okay? And then you can see here, here's the 3 parameters I use: the decat temperature, the relative airflow, and the relative catalyst inventory. And you can see by far the one that makes the biggest difference is the decat temperature. And then secondly is if I run excess oxygen. Okay? And these are the only ones that are getting down to 0.1%. And that's kind of where I'm looking for, right? I'd like to send a 1% carbon catalyst back to my riser, all right? And look at the temperatures, 780, 795, 804. Those are high temperatures. Those are a little bit dangerous for zeolite hydrothermal stability. Okay, so that's a little bit of an alarm bell with this high temperature carbon species. Now for the CO production, the flue gas composition works exactly like you would expect as you increase. Okay, obviously, as you increase the carbon on catalyst, you've got more excess oxygen coming out. As you increase the air factor, you've got more excess oxygen coming out. No news there. CO2 is the opposite of that. CO is all really, really low. Now remember, this is a little 5-ton per day demonstration unit. So the mixing's pretty good. The CO combustion is happening. It's fine. Right? These are very low CO numbers. In a commercial unit, would that be the case? It might be alarming, except, here's the important point, commercial BFCC units are always going to be smaller than FCC units because you're only going to size it for the wood basket that you can afford to send to feed it, right? So if you were running a 2,500 ton a day unit, which is a good design basis, at maximum yield, that's the equivalent of a 7,500 barrel a day FCC unit. That's tiny. So the whole idea in all of this, and it was in Kior, was that we'd have a whole bunch of these and they're feeding a central processing unit. Okay? So really I'm not worried about afterburn. Not like what we heard from Rob with the 89,000 barrels a day unit. You know, this is not in that league. Okay, real quickly about the phosphorus promoted catalyst. Guess what? We found out that made a difference. And as I said, all ZSM5 in my experience should be phosphated. And I didn't really know this, but the phosphation changed the coke combustion. And the way in which it changed it largely is it eliminated the high temperature peak. Now, this peak shifted up a little bit, but the peak up here is essentially gone, okay? CO-CO2 ratio changed too. We need to plug all these things into the Barracuda model, but still, it's interesting. Maybe the phosphorus is making coke combustion more facile, right? And it also helps me eliminate 5 reactions or 4 reactions, which definitely helps it compute faster, right? And this is ongoing right now. I wish I had results to share with you guys, but we're just not there yet. Okay, conclusions. The initial results indicate that excess temperatures could be needed to reduce ECAT below, carbon on catalyst below 0.1%. Initial temperature 780. Like I said, that's alarming, right? So you've got a trade-off. ECAT activity back to the riser versus long-term hydrothermal deactivation of zeolite, which is also activity. So that, if you're really serious about this process, that needs to be explored. Right, and the full analysis would, of course, include the complete FCC unit with the proper heat balance, right? At demo scale, the risk of afterburn is low. We probably need to commit commercial scale. Phosphorus-promoted catalyst, I just told you guys, essentially, it looks promising, but the Barracuda comparison is underway. Future work, our guys at NETL are actually going to build the first MFIX-EXA model of probably first this demonstration reactor, but then to go to a semi-commercial scale or commercial scale reactor, which is kind of exciting because it'll be the first, to my knowledge, exascale, model of a regenerator. And of course, we can put all kinds of hardware details and things like that into that kind of a regenerator. Look, I'm a big Barracuda fan. Do I think it's going to actually add anything? I really don't, but it is a nice objective for the exascale program, okay? And then finally, here's the acknowledgments. These are the people basically in the ChemCat Bio Consortium who have contributed to various pieces of data that went into this work. It didn't go in, it wasn't generated for us in CCPC, but we certainly made use of it, okay, because we don't run experiments. We basically look at all the programs in the National Lab System and see what we can use to accomplish our objectives. And then the work was funded by DOE's Bioenergy Technology Office. Okay, thank you.